Assalamu alaikum everyone. Welcome to the course of Real-Time Embedded System. Today we will continue our chapter number 6, that is of interfacing, and today is our lecture number 18. In previous lecture we talked about buses, we talked about wires, we talked about address input output, we talked about bus based input output, we talked about port based input output, we talked about control protocol in which we discussed STORP, and we discussed handshake and compromise between handshake. We talked about peripheral connections. So we are going to continue this chapter number 18 and we will look into some more interfacing options. So let's start this chapter. So in this slide we will talk about the bus based input output. So basically we have two types of bus based input output. Number one is known as memory based input output, and number two is known as standard input output, which is also known as mapped input output or input output mapped input output. So processor talks to both memory and peripheral using same bus. So we have two ways to talk to peripherals, which I have already told you. Number one is memory mapped and number two is standard I/O. In memory mapped input output, peripheral registers occupy addresses in the same address space as memory. For example, bus has 16 bits address. So 16 bit means like 2 raised to the power 16. So we will have 65536, which means 64K. So lower 32K addresses may correspond to memory and upper 32K addresses correspond to peripherals. So peripheral register occupy address in the same address space as memory. Whereas in standard I/O or I/O mapped input output, additional pins M/input output, that is mapped input output on bus, indicate whether a memory or peripheral access. So we have an additional pin that indicates whether it's a memory access or peripheral access. For example, if we have the same bus, there is 16-bit address, all 64 addresses correspond to memory when this pin M/IO is set to 0, and all 64K addresses correspond to peripherals when this pin M/IO is set to 0. So let's move on to next slide. So these slides include further details of comparison between memory mapped I/O and standard I/O. Memory mapped I/O requires no special instructions. Assembly instruction involving memory like move and work with peripherals as well. So we do not need any other instruction like move, add, work well with peripherals. Standard input output requires special instruction, for example in, out, to move data between peripheral register and memory. So there is a difference between these two. In one we require special instruction, in one we do not require any special instruction. We can work with move and standard instruction. Whereas in standard input output, no loss of memory addresses to peripherals. So this is the advantage of standard input output, no loss of memory address space. So we have seen that all the 64K can be used for memory and all the 64 can be used for peripherals. So no loss of memory addresses to peripherals. Simpler address decoding logic in peripheral possible. So we can have simpler address decoding because we are using either it for the peripherals or we are using it for the memory. When number of peripherals much smaller than address space, if we have very small number of peripherals compared to the address space, the higher addresses can be ignored. Smaller and or faster comparators. So as long as the peripheral requires less address space, it will be far smaller and faster comparator. So it means that we can compare it quickly. So these are the two advantages of I/O based standard input output, and before that I talked about the memory mapped I/O advantage, that we do not require any additional instruction. So let's move on to next slide. So in this slide we will talk about microprocessor interfacing interrupts. Suppose a peripheral occasionally receives data which must be serviced by processors. So what is happening? Peripheral is receiving data which must be processed by the processor or serviced by the processor. The processor can poll the peripheral regularly to see if data has arrived. So one way of checking whether the data is present or not by checking it after some time, and we call this as polling technique. The second one is that the peripheral can interrupt the processor when it has the data. So whenever the peripheral has data, it can raise some signal or it can alert the processor that it has data. So let's service the data. So we call this interrupt. So we have two things by which we can service the request of the peripherals. Number one is poll and number two is interrupt. Now this requires an extra pin or pins. So normally for interrupt we have INT pin. If INT is 1, processor suspends current program. So whatever the processor was doing, if interrupt is 1, it means the interrupt pin is high. We will suspend the program. We will jump to the interrupt service routine, which is also known as ISR, and then we start executing those interrupt service routine instruction. We also call it interrupt driven IO. So whenever we are going to use interrupt, it is known as interrupt driven IO. So the peripheral is working on the phenomena of interrupts. Essentially, polling of the interrupt pin is built into the hardware, so no extra time. So we do not require any extra hardware, it is built into the hardware, so it will save time. So there is no polling required here. Okay. So when we have to check the interrupt, it will build into the hardware. So no extra time checking for the polling. So let's move on to the next slide. So in previous slide I told you that polling of interrupt pin is built into the hardware, so no extra time or no extra cycle is required. It means that we are not going to poll at the end of every instruction. So this phenomena is kind of built in onto the hardware. So in this slide we are going to talk about microprocessor interfacing interrupts. So what is the address of the interrupt service routine? So address is usually known as interrupt address vector. Okay, so keep in mind whenever we have address, it means interrupt address vector of the ISR of the interrupt service routine. So there are basically three types of addresses. Number one, fixed interrupt. Number two, vector interrupt. And then we have compromise interrupt address table. So we have three types of interrupts. In fixed interrupt, address built into microprocessor. So we have a fixed address that is built onto the microprocessor and that cannot be changed. Either interrupt service routine stored at address or jump to actual ISR stored if not enough bytes available. So the interrupt service routine will be stored at some particular address, or if we are short of like memory, so we will jump to the actual ISR. So this is fixed, in which the address is built into the microprocessor. Whereas in vector interrupt, peripheral must provide the address. So we have to provide the address. The address is not constant here. It will keep on changing. Common when microprocessor has multiple peripherals connected to a system bus. So whenever we have multiple peripherals connected to a system bus, we will have different addresses. So in that case we will use vector interrupt. We normally prefer fixed interrupt when we have only single peripherals. In case of multiple peripherals, we recommend vector interrupt. And then there is a compromise, and that is known as interrupt address table. So we have a table in which we are storing the addresses of the interrupt service routines. So that is the compromise. So these are three types of interrupts. Let's move on to next slide. So in this slide we are going to talk about the interrupt driven IO using fixed interrupt service routine location. So this is the time, and you can see here that 1A, 1B, 2, 3, 4A, 4B and 5. This is usually called the cycles. That is how much cycles are required to process the request of the peripherals. So as I've told you, we usually call interrupt driven IO, and the other one is polling. So in this we are going to discuss how the interrupt driven IO work in the case of fixed ISR location. So how it starts, let's start from here. 1A, microprocessor is executing some program. At the same time, P1 is basically the port, receive input, or you can say it's a peripheral, receives input data in a register with address 0 cross 8000. So P1 receives input data in that particular register. So what P1 does in the second step, it generates a signal or assert into the request. So this signal is asserted, that is interrupt signal is asserted, so processor can provide services. In third, after completing instruction at 100, so the microprocessor was executing the instruction number 100, microprocessor sees the interrupt asserted by P1, save the PC value of 100 and set PC to ISR fixed location. So we have fixed location for this service routine, and that is 16. So what the microprocessor is going to do, it's going to complete the instruction, it's going to save the program counter address, it's going to see the interrupt is asserted, and then finally it will set the program counter to the value of ISR, which is fixed. In next 4A, the interrupt service routine reads data from this particular location from the register, modifies the data and writes the resulting data to 0 cross 8001. In next cycle 4B, after being read, now after reading this address 0 cross 800, P1 deserts. So now we are like the signal is going down, or we can say that the enable signal is turned off. While in final stage, that is fifth cycle, the ISR returns to normal routine where it will execute its normal operation, and the CPU will execute the next instruction, and it will load its program counter with 100 plus 1 because it left the program counter at 100. So now we are going to look at this example of interrupt based IO using fixed ISR with the help of timing diagram. So let's see this in next slide. So here in the initial stage you can see that we have a program memory, we have microprocessor, we have data memory, we have port 1, we have port 2, and we have register in port 1, we have register in port 2, and the register 1 address is 0x8000, whereas it's 0x8001, and both these ports are connected to system bus, which is connected to microprocessor, and we can see that the P1 port is connected to microprocessor directly, and it has this signal interrupt, and the microprocessor is holding the program counter address. This is main program starting from instruction 100 and then next instruction, and this is our interrupt service routine which is saved in program memory. It has fixed location, that is starting from 16, 17, 18, 19. So what happens in the beginning, microprocessor is executing its main program, Now in second, P1 receives input data in a register with address 0x8000. So this is the data that P1 receives. In next step, in the second cycle, P1 inserts in to request servicing by the microprocessor. So this signal goes high. As you can see here, the interrupt signal is now 1. Interrupt shortcut is INT. And we know that in next stage, what is going to happen? The program counter is going to save the value 100, and then it will move to interrupt service routine, and it will start from location number 16. That is our fixed location. So after completing instruction at 100, microprocessor sees interrupt asserted, INT asserted, saves the PC value of 100 and sets PC to ISR. That is our interrupt service routine, fixed location of 16. In 4A, the ISR reads from 0x8000, modifies the data and write the resulting data to 0x8001. So if we see in our interrupt service routine, so it is moving the data from this memory location, not memory location, that is the register location 0x800 to R0, then it modifies R0, and then we finally moves the value of R0 into this address 0x8001. So what happens? We read the data, we modify it, and then we are writing the resulting data at that particular location. And then finally return interrupt, that is interrupt service routine return. So once this happen, what is going to happen in the same clock cycle 4B? After being read, P1 deasserts. So you can see that now our interrupt is 0. Okay, so this is the whole diagram showing P1 going from here coming to microprocessor, and then for writing coming from microprocessor using the system bus, and in port 2 it is writing. So once it is done, we will have interrupt 0, and in next stage we are loading program counter with 100 plus 1 when microprocessor resume executing. So in this slide we will talk about a more complex memory protocol. So on the right side you can see that we have a finite state machine description with lots of control bits: ADSP, ADSC, ADV, OE, address C. Then we have these outputs and input go, and go is equal to 1, go is equal to 0, and then we have states S0, S1, S2 and S3. So S0 is the star and that is ready here at S3. So what is happening? Generates control signal. So what we are doing here, we are generating control signal to drive this particular memory chip TC55325FF memory chip in burst mode. Okay, so what we are going to do, we are going to use this IC in burst mode. So adder 0 is starting address input to device. So this is the starting address that will be input to the device. As you can see here, we have adder 0 to 15, which means that it is 16-bit address. Go is enable and disable input to device. So specification for a single read operation. So we have a clock, we have this signal ADSP, we have this signal ADC, we have this signal ADV, and then we are reading the address. So address is read in the first clock cycle. You can see here that in first clock cycle we are reading the address, and then there is nothing right because we are performing the operation of reading. So in /OE something gets enabled at the third clock cycle. Then we have these signals CS1, CS2, and these signals are on low states, then we have signal C as 3, and finally we are picking up the data for read in the third clock cycle. So data is read on the third clock cycle when we have enable. So this is how like memory protocol works for this particular chip. So this particular chip, the ISA bus protocol introduced earlier in previous slides, support standard input output. So I told you that standard input output is IO mapped IO. The IO read bus cycle was shown with the help of diagram. So in previous chapter I've told you like how ISA bus protocol works. In this example we will build finite state machine, as I've told you, controller that will generate all the necessary control signals. So this finite state machine is basically generating all the necessary control signals to drive chip in burst mode. So what is burst mode? Burst mode means that we are reading in pipeline. So I have already told you what is pipelining. So we are reading the data in pipeline. The input to our machine is clock. So to this finite state machine, the input is clock, and starting address I've already told you is added 0, and enable disable signal, that is go. The output of our machine is a set of control signals specific to memory device. So what is the output? I've already told you that it is like set of control signals. Okay, so this is how you read data in burst mode. So that was just journal about like what is finite state machine, what are states, and how we are going to read this particular memory chip in burst mode. So that was about the complex memory protocol. So that was it for today's lecture. Thank you very much.